So first of all, my apologies for not being able to visit Guangzhou in person and give this talk due to some visa restrictions. So this is joint work with Ian McCoy at MIT Lincoln Lab, and I'm Jiayu Xu at Oregon State University. So this talk is again about password authenticated key exchange, or PAKE. And I believe in the previous two talks in this session, so both talks mentioned the concept of PAKE. So I guess I'm just reviewing this thing. So in a PAKE protocol, there are two parties, and both of them hold a low entropy string called a password, and they interact with each other. And at the end of their interaction, they output a high entropy session key. So one thing to stress is that this is in the so-called password-only setting, and which means that the only information shared by these two parties in advance is this low entropy password. And in particular, this protocol does not rely on the public key infrastructure. And so there's an unavoidable attack for PAKE protocols, which is the man-in-the-middle adversary can always guess a password and then impersonate one party and interact with the other. So if this password guess is correct, then at the end of their interaction, the adversary knows the other party's key. So this is unavoidable. And the PAKE security notion basically says this so-called online guessing attack is the only attack that is possible. And of course, if you use this PAKE protocol in I guess IoT or wireless settings, then it is probably okay. But in the traditional client-server setting for authentication, this is simply unfit because the client can memorize the password in its brain, but the server should never store the plain password. So in the client-server setting, we need something stronger, and this is called strong asymmetric PAKE, or SA-PAKE. So the setting is this. So again, the client holds a plain password, but this time the server should hold a one-way function of the password. And again, they interact with each other, and eventually they output the shared session key. So the security notion for SA-PAKE is more complicated. So there are three unavoidable attacks here. So the first one is online guessing attack, just as in PAKE protocols. The second one is if the adversary compromises the server and steals what is stored in the server, which is f of password. So in this case, then recall that the password has low entropy, so the adversary can always brute force over the password dictionary, the set of all possible passwords. And the adversary, in this way, it can eventually find the password in polynomial time. So strong asymmetric PAKE requires that this offline dictionary attack can be done only after compromising the server. And there's something weaker called asymmetric PAKE, which is part of this offline attack can be done before server compromise. So this is the second attack. And then the third attack is if the adversary compromises the server, even without an offline dictionary attack, the adversary can still impersonate the server and interact with the client. So this is also unavoidable. So the security of SA-PAKE basically says these three unavoidable attacks are the only attacks possible. And the concrete security definitions for PAKE and strong asymmetric PAKE. So there are two types of definitions. The first one is the so-called game-based definition. So this is the traditional and I guess most simpler definition. And the other is universally composable, or UC definition. So over the years, UC has kind of superseded game-based definitions and became the standard for PAKE and also SA-PAKE. So because, first of all, in MPC in general, I guess UC is stronger than game-based in that it always supports arbitrary composition. And for password protocols, there's an additional advantage of UC, which is because Homo sapiens do this stupid thing, which is they always use the same password across different accounts. And this is taken into account in the UC definition and not in the game-based definition. UC has become the standard security definition. And so this work is focuses on strong APEC. So strong APEC this concept was first proposed in 2018, and it has proven very difficult to construct. So up to now, excluding this work, so there have been only 5 APEC protocols. All of those have been proven secure in the UC framework. But so this is a table that shows the client computational cost, the server computational cost, the round complexity, the level of security, the underlying assumptions, and the idealized model. So I will explain this very soon, but the bottom line is actually all of these 5 existing APEC protocols have significant issues. So let's take a look one by one. So these 3, the original paper that proposed OPEC, that paper proposed also two APEC protocols. One is called OPEC, and the other, some people call it OPEC Prime. And also there's this paper that proposed another APEC protocol called ORC-PACE. So all these 3 have the same 2 problems. The first one is, if you look at the UC functionality that they realize, so they don't realize the natural APEC functionality that you would imagine. Instead, they only realize a contrived, relaxed UC functionality, which contains some artificial relax of the standard, the full version of the UC APEC functionality. So this is their security level is actually weaker. And the second problem is all these 3 rely on a very strong assumption called one more gap diffie-Hellman. So this thing, I don't think it is used in many other protocols. I guess for the main reason is this is simply too strong. So these are the 2 weaknesses of these 3 protocols. This one, so this is by Bradley, Yarotsky, and myself. So this the problem with this one, the main problem is it is not very efficient. And there's a second problem is its offline security analysis is in the form of, first of all, it's in the general group model. And second, the analysis is in the form of the adversary can test a constant number of passwords for general group model operation. And this is, you can say this is not super useful in practice, because what if this constant is a billion? So it only says, okay, so it's all 1 passwords, but it doesn't tell you what this constant exactly is. So this is this one. And then there's this new APEC protocol. Actually, it achieves something stronger called SIPEC. But for our purpose, let's say it is an SIPEC protocol. So this CRISP protocol, the main problem is with this one is it uses a bilinear map, and this pretty much kills the efficiency. And the second problem is in the analysis, in the security analysis, it actually uses a general group model in a pairing group. And this thing itself, using the GGM in the pairing group, this thing is kind of problematic in itself. So I forgot to add a reference here, but there's a paper in also Asiacrypt 2010, which points out the problem here. So all these 5 existing protocols have some problems. And here's another thing. So PIKE under post-quantum assumptions is a very poorly studied area. So even for PIKE, there are not too many such protocols that have been proposed. And for SAPEC, there are simply no SAPEC protocols under post-quantum assumptions. This thing simply does not exist. So here's our contribution. So the first so we propose 2 new SAPEC constructions. So we call them compilers because both of them take UC PIKE protocols and compile the UC PIKE protocol into a UC SAPEC protocol. One of them is based on the traditional Diffie-Hellman type assumption, and the other is based on a type of post-quantum assumptions called group action assumptions. And so we pretty much overcome most of the disadvantages of existing protocols. So we realize the full UC SAPEC functionality. Our security analysis is based on mild assumptions. One is based on CDH, and the other is based on the group action version of CDH called GACDH. And we present a precise offline security analysis. So we say after compromising the server, the adversary can test 2 passwords per GDM operation rather than constant or O1. So here we are precise. We say 2 passwords. Our protocol is very efficient and also conceptually simple. So we do have one, I would say, also significant drawback, which is the offline security analysis is in the GGM. I guess this is kind of okay, but our online security analysis is based on this algebraic group model. So and it is pretty well known that CDH in AGM is equivalent to discrete logarithm in AGM. So you can also say that the security is kind of DL plus AGM. And interestingly, so opaque is based on one more gap Diffie-Hellman. And even in the AGM, it is not known whether this thing is equivalent to the discrete logarithm assumption. So basically, even though our analysis is in the AGM, so it is still not comparable with opaque. So this is the previous comparison table with our protocols added. So again, we have efficiency and we realize the full UC functionality. We are based on mild assumptions, but the online security analysis is in the AGM. So here's a very high-level idea behind the construction of our protocol. So I will only present the idea of the first protocol, which is Diffie-Hellman based. And the idea behind the protocol, the group action-based protocol is kind of similar, and I don't think I have the time to cover it here. So the starting point is this super naive protocol like this. So this is very similar to Diffie-Hellman. The server stores G to hash of password. So hash of password is H. Okay, server stores G to H. The server samples a random integer R and sends G to R to the client. And then these two parties agree on the key, which is G to HR. What is the problem with this? So the problem is, if you have an eavesdropper who sees this G to R, this message, the sole message sent between the two parties, then because password has low entropy, so hash of password also has low entropy. So this means that if you know this R, then R to the power of H, this session key has low entropy. So this is not a secure APEC. But the good thing about this is, so here, eventually the two parties agree upon a low entropy secret. So now what you can do is, you can add a PEC and boost this low entropy secret into a high entropy secret. So you enter this G to HR as the password in PEC. And then PEC will output a high entropy session key. So the problem with this is, so the adversary, even before compromising the server, it can pre-compute X and G to hash of X for all possible passwords X. And in this way, after server compromise, the server can look over the table and then recover X fast. So recover the password fast. So it turns out that this is an APEC, but not a strong APEC, because part of the offline attack can be done before server compromise. So what should you do? So what you should do is you need to change this fixed base G to a variable base S. And this pretty much kills the pre-computation attack, because before server compromise, you don't know this S. You don't know S, so you cannot compute the table. So this is a strong asymmetric PEC. So there's only one caveat, which is the server compromise, the adversary sees S and S to H. So the adversary can effectively impersonate the server by running the server algorithm on some S to the power of R star and S to H, this thing to the power of R star. And this has the same effect as a normal impersonation attack. But the UC simulator cannot detect that the adversary is doing this, assuming that DDH is hard in the group. But we overcome this in the algebraic group model. So in the algebraic group model, when the adversary comes up with S to the power of R star, the adversary needs to tell the simulator what R star is. And in this way, we can correctly simulate this impersonation attack. The offline security analysis, basically, it is like this. So the offline security essentially says, given S and S to the H, where H has low entropy. Recall H is heart of password, and password has low entropy. So this thing has low entropy. Then you ask, how long does it take to recover this H? So I call this thing discrete logarithm over a sparse set. And this turns out that the analysis of this thing is highly non-trivial. And it was first studied by in a paper by Schnorr in 2001. Actually, this paper, Bradley, Yarsky, and myself, this paper uses a similar idea, but basically it didn't open up the proof by Schnorr, and it only looked at the theorem statement in Schnorr's paper. And the theorem statement says that you can only test a constant number of values per GGM operation. And here, what we basically did is we opened up Schnorr's proof and really read and understood it. And it turns out that you can replace this constant with 2. So for every GGM operation, you can only test 2 values. So in summary, we present 2 new Asiacrypt protocols. The first one is Diffie-Hellman based, and it is proven secure under CDH and in the random oracle model. And offline security analysis relies on the GGM, and online security analysis relies on the AGM. And the analogous one is the group action-based protocol. This is post-quantum. And the idealized models and the assumptions are basically the group action version of the previous protocol. So again, our protocols are conceptually simple and more efficient than, I would say, most existing protocols. Okay, so this is the end of the talk. And if you are interested, then you can check out our paper on ePrint. Thank you.
Nice talk. And the question is about your general framework. Since it's not highly discussed, it's a very abstract framework. So have you think about these same ideas, within the different groups can be generalized to other post-quantum algebraic functions, say, for example, nuclear lattice space assembly? If you are moving to the big. No? No?
Hello. Yeah, so sorry, my apologies. I think the Wi-Fi here is that is my bad. My Wi-Fi here is not very good, but someone is trying to repeat the question for me. My apologies. Yeah. So yeah, so this is a good question. So here's the thing. So our protocol, I mean, our post-quantum protocol is a compiler from any UC pick to a UC SA pick based on group action assumptions. So basically, so you first you have a UC pick and you have some add-ons, and that add-on part is based on group action assumptions. But this UC pick, this part is black box. So it is possible that you do a UC pick based on lattice assumptions, and then in the add-on part you do group actions. And then the overall thing will be a UC strong APEC. So this is possible. So if I understood your question correctly, then yes, the answer is yes. So you can do lattice-based UC PEG, and then you do something else, which is group action-based.
This is the last one. Thank you very much. Thank you.